Hi, this is Dave Beasley. This is a talk I gave about the GIL at PyCodeConf in Miami 2011. It was originally recorded as audio only, but I've turned it into a screencast. Hope you enjoy.
I don't know why they scheduled this second in the conference, and maybe to make everybody depressed or something like that. Let's put like a global interpreter lock talk into the conference. What I wanted to do when I initially thought about this talk, if you know anything about me, I kind of blew the global interpreter lock up at PyCon 2010. You can find that online. And when I set this up, I was like, oh, I had to try to give like this like really pro GIL talk just to mess with people, you know, like talking about how awesome it was and so forth. So I sort of thought about this talk. It's like, let's have this talk about embracing the global interpreter lock. And then I sort of realized that would actually be the end of the talk. So that's pretty much the end of it. Well, the end of it is basically, I realized I would just end up writing a talk about multiprocessing or futures or something like that. So what I really want to talk about is actually this notion of embracing the idea that Python's global interpreter lock can be improved. So one of the things that you probably know is that the GIL comes up as a topic in a lot of places. People love to talk about it. Always comes up in discussions about the future of Python, whether it's on topic or not. I actually sometimes wonder whether it's Godwin's law of Python, in the notion that the second the GIL gets mentioned, the discussion just dies, and like the core developers like close up their ears and go focus on something else. I'm hoping that this doesn't shut down the rest of the conference just by mentioning it. But it is a topic that comes up kind of in the future of Python. Just so you know, my interest in the GIL is mainly as a fun hobby. I mean, that might sound kind of weird, but you know, I'm an ex-academic. I used to teach operating systems at the university. And I think looking at this is just a fun systems project. It's like, you know, I'll sit around and I'm thinking, oh, I'm bored. Oh, let's go break GILs today with like new corner cases. I think it's just really cool because you're starting to see all these like interactions between things like multiple cores and crazy things on your systems, you know, cores fighting with each other and sort of pathological performance cases. I think it's really fun just to look at that. So if you're wondering like my motivation on it, that's really it. It's kind of cool to look at that stuff. And I think one of the things that I would like to just throw out there as a premise, one of the reasons why I think the GIL is interesting is that threads are actually a useful thing. I know there's a lot of people that love to hate on threads. I mean, you know, like you talk to the Twisted guys, and they're just like, don't use threads, use Twisted. Or you talk to a lot of the async guys, you know, G-event, event list, stack list, that kind of stuff. There's a lot of this like avoidance of threads. But you know, even if you take that into account, threads are being used by people. I mean, like if they weren't being used, nobody would care about the GIL. Like it wouldn't even be a topic of conversation if people didn't want to use threads for things. And it turns out that threads are actually used for a lot of stuff behind the scenes, like multiprocessing uses threads. A lot of these messaging libraries use threads. There's actually a lot of uses of threads that sit in the background, even if you're not using them as a programmer. Like if you're not programming directly with threads, threads are often there. And they're often there to solve problems. This is Chicago last February, by the way. Maybe this is this is Lakeshore Drive in Chicago. I don't know what this is illustrating. Maybe blocking problem in async or something like that. You know, threads are actually used by a lot of these libraries just to solve like tricky problems, like blocking problems, long-running calculations, things of that nature. This is also a subtle advertisement to come to Chicago to take a class. So if you're not happy with Miami, you can come up there. So what I wanted to do, I've talked quite a bit about the GIL in the past, and I didn't want to really repeat a lot of that, but I wanted just to kind of talk about it in a nutshell, and then do some experiments along the lines of that you can probably improve the GIL, or there's opportunities for improvement. So if you're not sort of familiar with the global interpreter lock, or really what that's about, the gist of it is that every Python program that you write gets compiled down into some virtual machine instructions. You can actually see those if you use Python's dis module will show you the disassembly of your Python code. And really what the gist of the GIL is that you can't execute those instructions concurrently. I mean, the Python interpreter is written in C. The execution of those instructions takes place in C a lot of times. And basically, you just can't run concurrent instructions. And so there's a lock that protects that. And what that lock is doing is essentially protecting the Python interpreter implementation. I mean, Python is written in C. There's a lot of low-level bookkeeping, memory management, data structure updates, and so forth. And that's why that lock is there. I mean, essentially, it's protecting things like reference count updates. It's protecting updates to mutable data types, like lists and dicts and sets and things. There's some internal bookkeeping. There's a ton of C extensions for Python that are often not written with thread safety in mind. The GIL actually protects those. And so this is a lot of very low-level stuff. I actually think that the GIL is actually a good thing. I mean, if you did not have this, the implementation of CPython would be significantly more complicated. I mean, it would greatly complicate things. It would probably frustrate the core developers like so much that at some point they would just reach the breaking point, remove Python from the web and like disappear or something like that. It's probably good that it's there. But there are some issues with it. I mean, if you know anything about the GIL, one limitation of it is you can't use threads for using multiple CPUs. So if you're trying to turn, like your 4-core laptop into a supercomputer or something like that, threads is not the way to do that in Python. I mean, you don't get an advantage there. Some other things with the GIL has to do with uninterruptible instructions. It turns out that some of these instructions, depending on what it is, might take a very long time to run. These are kind of corner cases, but like an example might be, okay, I'm going to do a find on a string, and oh, the string happens to be 3 gigabytes. Okay, it might take a while to like scan through that. And it turns out that certain instructions you can't interrupt, and you can get like hiccups in your program. So that's another limitation. And then another thing that I'm going to talk more about here is just there's bad behavior when you have CPU-bound threads in your program. This is something that's known. People have been working on that. So what I want to do is just talk a little bit about this challenge of can you actually improve the GIL? Because I don't think it's going to go away anytime soon. I mean, there's proposals to do things with it, but it's a really tricky problem. It's probably not going to go away. And if it's not going to go away, what can you do to improve it? I mean, are there things you can do to it? Can you embrace the idea that you can improve it? And so forth. So what I want to do is actually just talk about an experiment. I'm going to try to do a live demo and just talk about an example of something that can be improved. And essentially what the experiment I'm going to talk about is something involving message passing or messaging. It's essentially an experiment where you have a client and server sending size prefixed messages to each other. This is the kind of thing that you would do if you were messing around with something like 0MQ or some of these messaging libraries. And essentially the message here is that you have some header on it and then a payload. And what I'm going to do is well, one of the things you can ask is, well, why this experiment? One of the reasons why I'm talking about it is that messaging comes up in a lot of places. A lot of people are thinking about messaging in terms of like scaling their code out. It involves I/O. It's often used as an alternative for working around the GIL. Like if you're working with the multiprocessing module, you're working with messaging. Okay, so it is used for a variety of things. And so I definitely wanted to look at it. And the little test that I'm going to do is essentially this. I wanted to make like a really, really minimal test of just like a receive reply. So what I've got, and this is pseudocode, by the way. I have a server. All it does is gets a message, echoes it back. Not a very interesting server, but we're just going for minimalism. And then I have a client that is just going to send a message, receive a response, and because I didn't want it to be completely evil, I thought it would make it sleep a little bit too. One of the things that I didn't want to get into is making this a messaging stress test. So this is like cruising at like slow speed on the interstate here. It's like send a message, get a reply, chill out for a little bit, go send another message. And so what we're going to do is try this little test. And I'm going to show you some results with actually 5 different implementations of a server. One is completely written in C with 0MQ. The reason I include that is I wanted to have like a baseline of something that would probably be really fast and not involve the GIL and not involve Python. And then I'm going to look at 4 implementations that involve Python in different ways. One emphasis here, this is not a messaging stress test. I'm not trying to see how fast I can send, like how many messages I can send per second or anything like that. I'm just trying to see sort of what happens here. As far as doing the hardware on this, I did all this work on an 8 CPU EC2 instance. So they have like these extra large compute intensive instances. 64-bit, it's Linux, it has a lot of memory, has high I/O throughput. It's not my laptop. Okay, so this is like something out in the cloud, not the like micro instance or anything like that. And the test that I'm going to do was just this thing where I was going to say, well, I'm just going to send 10,000 8K messages back and forth. So 10,000 messages, there's a 1 millisecond delay after every message, not a stress test. And we're just going to see sort of what happens here. So the first test that I did was really this example of just doing this on an unloaded machine. Client server, nothing else running. How long is it going to take to do that? Now, if you sort of think about this scenario here, it's basically I'm sending a message, I'm getting a response, I'm going to wait a millisecond. If you work the math out, you're essentially looking at, this is probably going to take about 10 seconds. It's probably going to take a little bit more than 10 seconds because there's at least 10 seconds of just sleeping with this delay in there. And if you do this test, the results are actually about what you would expect. It's a little bit more than 10 seconds. I would actually claim that most of these results are essentially the same as each other. I mean, and you could argue why is like 0MQ a second slower or something like that. I don't really know. But you see, you sort of see results like that where it's, okay, it takes a little bit longer than a second. I can actually do that sort of thing on my laptop. I mean, this is the Mac that I'm using up here is a quad-core Mac Pro. It has 8 gig of RAM. It's not running anything at the moment here. And if you run one of these tests, I'll just sort of show you one of these in action here, just to do a live demo. You'll see this thing running, and if you look at the process monitor, I don't know if you can see this, but it's using about maybe 8 to 10% of the CPU. It's not heavily loading the machine. And it should finish up. Okay, it finished up in about 13 seconds. Okay, so it's a comparable result to what's in the slide. And so this is sort of a simple test. And one of the things that you can start to ask is, what happens if you introduce a thread into the picture? Okay, so I'm going to do a test where I introduce one CPU-bound thread into the picture. I don't know what that thread is. In light of recent internet discussion, it's probably Fibonacci number, but you know, it's something important, like critically important there. And you can ask this question of like, well, what does that do to the performance of the test code? And the results are actually sort of I would say sort of shockingly bad. I mean, one of the things that you find is that the C version of code is essentially unaffected by that. But if you go to the Python versions of this, you take this huge hit. I mean, it essentially goes from like 10 seconds up to like 100 seconds or 140 seconds. Well, I'm just doing that, and you know, I can sort of try that here. I have the ability to run this server with one thread running. So what you're going to see in this case is, I don't know whether you'll be able to see that in the back, but it says Python 3 running at 100% CPU load. And if I try this messaging test, it's going to sit here for about 100 and some odd seconds. I'm not going to wait with dead air while it does that, but we'll come back to it in a second here. So I don't know what you think about that. I mean, is anybody kind of mildly horrified by it or concerned about it? I sort of have the opinion that like why can we let that stand? I mean, why is that an acceptable situation? And I would make the claim that you could probably do better than that. I mean, Python can probably optimize better than that. I would not claim that this is some weird micro optimization. You know, we're going to change lots of code and it's going to run 2% faster or something like that. There's a big window for speeding things up. And the other thing, just to emphasize, this was not a messaging stress test. I mean, this is like a lightly loaded messaging thing, a lot of sleeping, not hammering the system with messages. So I think it's definitely something to think about. I did try some other things. This is mostly for my own amusement, perhaps. I thought I would actually try PyPy with this. I'm going to have to apologize to Alex Gaynor in a second on this. So I actually downloaded PyPy 1.6, and I was like, oh, I wonder how long it would take PyPy to do that test. The results were very interesting. Took about 6,600 seconds with the blocking version of that. This is submitted as a bug report to the PyPy project, and just to be fair to them, it has been fixed on their trunk, on the trunk version of PyPy. I actually was not able to compile that on Linux, and I was not able to figure out why, but I've tried it on my Mac, and currently in PyPy it takes about 100 seconds. So it's definitely better than 6,600 seconds. The other thing that I thought I would try is just try Python 2.7. Keep in mind that all these tests are done with Python 3.2. You go back, if you just go back to the old version of Python, it actually gets a lot better. Python 2.7 does not have the performance penalty that Python 3.2 does, which is kind of an interesting little statistic, because apparently the GIL was, you know, if you know anything about Python 3, it was fixed. Python 3.2, there was a fix made to it. Maybe not a fix to everything. Okay, there's some room for improvement there. Okay, that's actually still running there. Okay, so oh, actually, did it finish? No, still running there. Another thing that you can try. I mean, so this is sort of interesting. Another thing that you can try is to try this with GUIs as well. I mean, one of the things that you might look at and say, okay, this is just Dave being evil with some network experiment and, like, you know, whatever. You can actually see some pretty interesting results if you try to match this stuff up with GUI programs. This is actually an experiment that you can kind of try on your own machine. I don't know, does anybody have Python 3 installed on there? 2 people? Is that? No. Sad. So okay. So there's my messaging test here, just finished up, 200 seconds. Well, here's kind of an interesting GUI experiment. Most of you probably don't use idle. Maybe you do, but it's essentially a development tool that comes with Python, has a GUI associated with it. If you just run it, you'll find that it's reasonably responsive. I mean, you can type code into it interactively. It helps if you can actually type correctly. Let's patch that up. Okay, so you can try some code. You can open Windows and so forth. It turns out that if you mix GUI programming with threads, especially CPU-bound threads, you can actually see the performance just go completely away in like a horrifying manner. One of the ways that you can try this is, I'll just do this interactively. So let's say you had like just some thread that's spinning here. Okay, it's not a very interesting thread, but you have a function that's just going to sit there and spin. And we'll just go ahead and like launch this thing. Okay, so this thing should be launched at this point. Okay, so if you're looking at the monitor there, I'm basically running 100% CPU, got a thread running. If you try to start like a GUI program, I'm going to launch idle kind of manually here. You actually find that it is just completely unusable. I mean, first of all, it's not even like coming up on the screen yet. Okay, so it's sitting there thinking about it. The other thing that you'll find is that you can barely even type into it. I'm actually typing right now. Okay, I've made some mistakes. Well, no, I guess I did make some mistakes. It's very slow. Like if you try to open a new window, it's sitting there thinking about it. The beach ball is now up. not impressive. I mean, it's basically unusable. I actually think it's kind of a bit of a problem because a lot of people use GUIs for like data visualization, data-intensive things. It might have threads going on in the background while they're doing something with a GUI. So that's another example. I mean, basically you get like horrifying performance if you try to do a GUI with thread. And one of the things you can ask is just, well, what is going on to make all of this bad? Like, why is messaging slow? Why are GUIs slow? And essentially what it is it has to do with the mechanism currently used to switch threads in Python. And internally in Python 3, it turns out that there's a severe penalty on interactive or things that demand like a high response time or a low response time. And what is happening is it turns out that in Python 3.2, the way that the GIL gets switched between threads is based on a timeout mechanism. This is a lot of information on one slide, but the gist of it is that if you have some thread that's running and another thread wants to run, like let's say you have a network packet that comes in. Okay, so this thread 2 is sitting there waiting, and it says, oh, I'm waiting for something on the network. When that data arrives, it actually has to wait 5 milliseconds to get the GIL back. It actually does like a timed wait, and it says, okay, I'm going to wait for 5 milliseconds. Once that's up, it will actually force the other thread to preempt itself. And what's happening in a lot of these network codes is that you're getting a buildup of these like 5 millisecond delays. I mean, essentially you're releasing the GIL or something wants that lock, and it has to wait 5 milliseconds every single time that it wants to do that. And that's actually what's happening in sort of the GUI example as well. You know, like GUIs are based on all these like mouse events, a lot of event handling. Every single time it wants to do something with an event, it has to wait 5 milliseconds to get it back from that CPU-bound thread. And just to kind of explain what is happening here, if you go back to this server code, what's really going on are these operations where you receive and send a message are actually surrounded by operations that release and reacquire the global interpreter lock. Because when you wait for a message, you're involving the operating system. You want to go to sleep. When the message comes in, you have to reacquire the GIL. It actually turns out it's a bit worse than this because this messaging example that I did is actually receiving like a message header as well. I mean, it says, give me a header. Then once you've got the header, give me the rest of the message. What you're doing is you're getting like a buildup of these sort of GIL release acquires, and you're just getting this huge buildup of these 5 millisecond delays. So that's actually what's happening in some of the network code is you're getting this, you're sort of hitting this like corner case of the implementation where it's not so good. And one way to fix this is to start introducing things like thread priorities. Just as a little bit of background, the original patch for the global interpreter lock in Python 3.2 actually had a priority scheme attached to it. For various reasons, that was not adopted. I mean, essentially, it actually ties in nicely with what Jesse said. Python community is very conservative about the changes that they make to the language, and a very conservative step was made on changing the GIL. They said, we're going to try a new scheduling thing, and we're just going to kind of see what happens. That's actually a decision I totally agree with, by the way. I mean, I don't think the core developers should just run in and totally rewrite the global interpreter lock with tons and tons and tons of magic. So taking it kind of slow and steady and studying it is probably the right way to go. But that patch did have a priority scheme on it. And I definitely think it's something that the Python community might want to revisit. I mean, if you look at some of these messaging tests, it's probably something worth looking at. And you can do some experiments with this. I actually have a version of Python that has like an experimental priority scheme in it. This is mainly just for a research project, just to sort of see what happens. And essentially what it is it's just a scheme where each thread has like a priority level, and then Python just runs the one with the highest priority. It's probably not suitable for real work, but it's just kind of a test bed for some stuff. And it has a mechanism where you can sort of set the priority manually and lower your priority if you want to. And it turns out that if you try this sort of thing, you actually get some really nice results with it. It turns out that if you try this with some of these like messaging systems, you actually see that performance penalty almost completely drop off. I mean, it's what happens is you actually get performance that's pretty comparable to the version without thread. It's better than Python 2.7. Okay, so you get a nice drop off there. The other thing that you get is things like GUIs actually work a lot better too. Like if you're in a graphical user interface, if you spawn off like a CPU-bound thread, you'll actually find that the GUI is actually completely usable. Like if I try this, I actually have a version of this already all ready to go here. So I'm going to run like a special version of Python 3 with priorities on my bad idle GUI here. You'll actually find that it's completely responsive to what I'm doing, even though the thing is like running at 100% CPU. Okay, so it's running along. It's running at 100 CPU. If you want to stress test it even more, I mean, you can increase the number of threads. Maybe I'll pick on Alex Gaynor. Give me a number between 1,000 and 2,000. 1,400? Okay. What I'm doing here is I'm running idle in competition with 1,400 CPU-bound threads. It's going to take a little bit of time to spawn up because it takes a lot of... Okay, so 900 threads, 1,000 threads, 1,400 threads. Okay, it took a little bit of time to come up. But it's completely responsive. Okay, so this thing is actually running 1,400 CPU-bound threads. The GUI is actually totally usable. It's not it doesn't look visibly slower to me than using it without threads. And the whole reason that that is working is that the GUI has a higher priority than all those threads. Just so you know, operating systems do not have problems running 1,400 thread on modern machines. I mean, it might not be a great idea to run 1,400 CPU threads, but it's not going to kill my presentation or anything. Famous last words here. Okay, so some thoughts about this. Mainly what I want to throw out there in this talk is really just this notion that you can make things better. I mean, this is just one example where, you know, that this priority scheme for Python was not a lot of code. It basically involved a couple changes to a few files. And by doing that, you know, you get huge improvements in things like GUIs, messaging, and so forth. And I'd really just like to throw out this idea. Is that the only thing that you can do? Is the GIL this like closed book where, well, the GIL sucks, we can't get rid of it, we can't make it better, why don't we just forget about it? I just can't accept that as an answer. I think there's opportunities for making it better, and there's a lot of neat stuff that people are thinking about in Python 3. So one other thing that I just wanted to throw out there, I mean, I don't really have time to talk about it, but this is actually something for the people doing async. A lot of people are doing event loops, async, coroutines, blocking, you know, non-blocking I/O. This is a thought experiment. Currently, Python actually releases the global interpreter lock on every I/O operation. Does that make sense in non-blocking I/O? Kind of have to think about it for a little bit. But if you're dealing with non-blocking I/O, you're not going to block. That's like it's part of the name of non-blocking I/O, right? Not block. So you can think about things like, well, should the global interpreter lock be released on non-blocking I/O? Maybe that's an opportunity for an optimization. And like you could go into the socket module. You could say, well, if you're in non-blocking I/O, we're just not going to release the GIL because A, we know it's not going to block. And the reason that you might not release it is, here's what you might get from that. You might actually get like a significant decrease in like system calls. You're not dealing with mutexes, condition variables. You know, why are you dealing with the operating system with all this locking stuff if you're not going to block? So those are the kinds of things that you can kind of think about. And then just sort of wrapping up. I don't know how I'm doing on time here. Pretty close on time. I think this is a neat problem that I hope Python programmers are interested in. I mean, I think you can do things here. I don't think you have to rewrite the whole Python core. I don't think you have to write your own operating system. And I think it's something that you can do with incremental improvements. So I think there's a lot of neat things you can do. As far as some final words, all the code for this and resources are online. I actually have like some, I don't know whether I can mention it at a Git. I have a Bitbucket repository. It's a clone of the CPython interpreter with some of the modifications in it. I've also posted the testing code if you're interested in just seeing what did Dave do in that talk. go there. And I'll also post a PDF of the slides at that point. So basically out of time. I don't know, I can probably have some time for some questions if there are any. If no questions at all.
I have a question.
Okay.
So you told me before that you've done some academic research. You used to be a professor. Have you written any academic papers about this topic that you have available?
This is actually a great question. I have not written an academic paper on this, but I think there is room for a very interesting academic paper here because, well, here's why I think this is interesting. There's actually many languages that have a global interpreter lock. Python does not have a monopoly on the global interpreter lock. Okay, I mean, I think Ruby has one. I think even Erlang has a global interpreter lock. Maybe not in the latest version, but they've had one. And one of the things that you're finding with these global interpreter locks is that actually these languages, in a sense, want to do thread scheduling. I mean, that's what really this problem is about. How do you schedule threads? How do you do priorities on threads? And I think one interesting question to ask is the thread library and the operating system giving enough assistance to these languages to do it? I think there's like an interesting, there might be an interesting space, almost as like an operating system project. You know, could operating systems give hints to languages with global interpreter locks about what's going on? Like, could an operating system give a hint saying, if you do that, I'm going to block, or I'm about to context switch you, or that sort of thing. I think there's like an interesting area for that. Part of that too. I mean, we had a very interesting session at PyCon 2 years ago when we talked about the GIL. There was an after-hours session that had about 50 people show up, including Guido and a whole bunch of other people. One of the things that I was amazed is a whole bunch of operating system kernel hackers showed up out of nowhere at this thing. We had these guys like, oh yeah, I worked on thread scheduling in HPUX or something. I'm like, where'd you? Like, you're at a PyCon, and there was this huge debate about how this was like so interesting from like a systems perspective, like scheduling and thread libraries and all that stuff. So I think there's a lot of neat stuff in there. If there's any students thinking about an interesting systems paper, I think
they should come to you then to ask you about.
Well, what should really happen is I should say that fixing the GIL is impossible, and then they should prove me wrong. That's the ideal situation.
And then very quickly, if the code that you have with the priorities, is that something that would be production runnable, or is that like not anywhere near
right now?
That
it's not production. It's not production run. I can tell you one problem with it is I can't get the threads to quit in it at the moment. It's just full disclosure. Yeah, like if I try to quit idle. Well, actually, that worked. I've had problems with idle not going away with like lots of threads, but actually in the priority thing, there's actually been a number of patches submitted for that in the bug tracker. I think there's probably like 4 or 5 different implementations of priorities.